I'm Mr. McBrien. This is SCH4U, ions, and paramagnetism. The Ontario curriculum would like us to be able to talk about the benefits of various aspects of atomic and molecular structure. We'll hit on a little bit of that today. They also want us to be able to discuss the characteristic properties of elements in the S, P, and D blocks of the periodic table. We'll spend a fair amount of time on this today. We've hinted at this several times already. The outer shell electrons and their properties explain many phenomena that we've been observing for centuries. Based on these characteristics of the outer shell electrons, we think we can explain multiple valences for transition metals, we can explain magnetism, and a different phenomenon, paramagnetism. The periodic table groups elements into groups or families, and they're arranged the way they are due to these highest level electron configurations. For example, if we fill the S and P orbitals, the configuration of this in the noble gases helps us understand why they don't react, why they're inert. They have complete outer energy shells. We can group similarly other kinds of compounds on that basis, the basis of similarity of their outer shell electrons and which sublevel of is involved in those outer shell electrons. So we have an s orbital that we can work with and 2 electrons that need to be placed in there. We have the p orbital and the 6 electrons that need to be placed in there, and so on. And we've discussed this before, but now we can look at the periodic table in a new way. And we can see that our alkali metals are over here with the s orbital being filled. We can see that our transition metals involve the filling of the d orbitals. We can move over to the right hand side and see the p orbitals being filled, and the lanthanides and actinides involve the filling of the f orbitals. So now we can actually see why the periodic table is grouped the way it is, and we can start to take these properties and look at them in a new light. So for example, we can start to look at the charges that result on favored ions and explain why they are there. And even better, we can start to understand why there are multiple charges on the transition metals. And the answer to this, of course, is that a full or a half-full sublevel is unusually stable, and so it'll favor ions that will result in this full or half-full sublevel. If we consider zinc, well, zinc 2 plus is formed when we take the neutral element and we kick out the 2s electrons. When we do this, we get a positive 2 charge because we remove 2 negative electrons. We have a stable ion that we can work with. Of course, it's quite unlikely that we're going to kick out all 10 of the d electrons. Now, in contrast, lead has multiple ionization states. If we look at its outer shell electrons, they look like this, with a pair of s electrons and 2 p electrons. No great surprise, we can kick out those 2p electrons and form lead 2 plus. However, the s electrons are similar in energy to this, and it doesn't take too much more to kick those out as well and form the 4 plus ion. And sure enough, we can observe those 2 ionization states, those 2 ions in nature, lead 2 plus and lead 4 plus. You can do a similar exercise with most of the metals in those in that D block, where you can predict the ionization states without having to look them up. We can also look at phenomena such as magnetism. So the magnetic properties of elements are attributed to the ability of atoms to orient themselves in the same direction. We've observed for centuries the fact that there are strongly magnetic elements like iron, nickel, and cobalt, and these closely packed atoms can orient themselves into domains or groups which augment each other's magnetic fields and can form what we call permanent magnets. These are ferromagnetic materials. The more atoms with the same orientation, the stronger the magnet. As it turns out, there are many more weakly magnetic substances, which we call paramagnetic substances. In these ones, what happens is individual atoms orient themselves, and only when in the presence of a strong magnetic field. We can actually rationalize this behavior based on unpaired electrons. So if we have a look at iron, for example, and nickel, these have several unpaired electrons. Iron with 4 unpaired electrons and 2 paired electrons. Nickel with 3 pairs and 2 unpaired ones. We call the paired electrons diamagnetic electrons. Unpaired electrons are called paramagnetic electrons. These elements exhibit strong magnetic behavior because they have a number of unpaired electrons. However, there are lots of paramagnetic elements, far more in fact, that have at least one unpaired electron. And as mentioned, in the presence of a magnetic field, that electron will orient itself and there will be a small attraction. So platinum, aluminum, and many other metals that we don't think of as magnetic have magnetic properties in the presence of a magnetic field, if it's strong enough. Now, in contrast, any materials that have no unpaired electrons, well, when all the electrons are paired, their spins cancel out. And when this happens, it isn't just that this is a non-magnetic material. In fact, it's repelled by a magnet. This force is weak. You need a very powerful magnetic field to observe it. But if you go online and have a look at this link, you can see a live frog being levitated inside a very powerful magnetic field. So in fact, it is an observable force that we get from it. Okay, so this quick discussion today simply looked at some of the outer shell electron phenomena that we can now explain based on what we know about the way these electrons are placed inside the orbitals. We can explain various ionization states of metals based on stable electron configurations. We can explain paramagnetism, the weak magnetic force that attracts some metals. And we can explain diamagnetism, the repulsion of certain other metals based on paired electrons. For your homework, please go ahead and do the worksheet and the paramagnetism activity, and don't forget to look over the note. If you'd like to do some more reading, there's some more excellent material on diamagnetism and paramagnetism online, and some very interesting movies and things that you can have a look at. Few activities as well. Thanks very much, and have a great night.